Up for our second presentation here, can the CAN bus fly? Risk of CAN bus networks with avionics systems. Patrick Kiley is going to be here. He's going to tell you all about it. Patrick, take it away.
Hey, I have no idea where that date came from, so just ignore that. So my name is Patrick Kiley. I've spent about 18 years in the information security industry, specialized in hardware and transportation security. About 10 years ago, I got interested in hacking cars, and because we have such a short time and running late, I'll just keep this story short. But my first experience is I had a BMW that I decided I wanted add an iPod interface to it, and I nearly managed to brick the car. So I learned from that point. That was a fun experience working with tools that are written in a different language, but I learned a lot, and I hopefully won't brick any more cars on my way to doing cool stuff. So, what we're going to talk about, just going to give you a little primer on avionics equipment, and then just a real quick primer on CAN bus. I realize this audience probably knows most about it, but it's relevant to the later stuff. And then we're going to talk about some of the basic instrumentation, how it comes through CAN bus, and how we can hack it. And then a really funky version of a multi-packet CAN bus that doesn't follow any standard whatsoever. And then a couple conclusions, and we'll be about our day. So, primer on avionics. This is basically just to introduce you to some of the terms that we'll use later, so we're not speaking above. And I apologize if there are any aviation people in the room that this is a really low level. So, airplane components. You have components that control roll, which is left and right, which is bank. Rudder, which is actually twisting around the y-axis, is like what you'd use in a car on the ground. Those are combined together to actually change an aircraft's direction. Elevators will basically make you go up and down in the sky. Flaps are devices that provide additional lift for takeoff and landing, and basically allow you to operate at lower air speeds to make landing and takeoff safer. And then trim is a term you'll hear used in aircraft, and that's basically used to equalize pressure. So when you're trying to climb out and you're under a certain power configuration, you'll actually trim out control pressure so you're not having to constantly pull back on a control. It basically equalizes that out, so it keeps you at that attitude. And then when you level off at speed, you'll adjust trim again. You'll have a different trim for landing, etc. Trims just neutralize any pressure so you don't have to keep constant pressure. Imagine if you were trying to go around a turn constantly, just having to keep a steering wheel constantly at an angle. You'd tire out pretty quickly, and that would get pretty annoying. It basically equalizes it out, so you really only need minimal control inputs to maintain attitude and heading. Now we're going to get into aviation components. So these are the components of an avionics system, a modern glass cockpit aviation system. The first one you'll see is an acronym called AHRS. That's Attitude Heading Reference System. That's basically the gyroscopes in the aircraft that detect acceleration and position in space. So if we're an aircraft and we're tilted up or tilted down or left or right, it'll display that appropriately on the instrumentation displays. Magnetometer, just a very technical term for a compass, basically detects the direction that you're traveling and the direction that you're pointing. Engine telemetry, so as opposed to cars, aircraft have a lot of engine telemetry. They have temperature probes on just about every single component of the aircraft. You'll have a bunch of different temperature sensors, a bunch of different pressure sensors, multiple different fuel sensors, both flow rate and fuel level. And you'll have something called a NavCom. NavCom is basically a combination radio and navigation receiver. A lot of older navigation aids actually work within the airband, and they transmit pulses that are able to be picked up on certain frequencies, so you can actually tell where you are in relation to these navigation aids. But it's the same device that you use to communicate via voice, also receives those radio broadcasts on the same airband. So typically the devices that capture those are the same device, and they're called a NavCom. Transponder. So everyone has seen a display where you have a radar and you have a radar scope and you see all the little blips on a scope. What a transponder does is it actually enhances that signal, so you don't need to send out as strong of a radio pulse when a radio pulse sweeps across an aircraft, the aircraft will respond with a specific encoded message that will identify the aircraft's name and number through what's called a standard like an ICAO, as well as a squawk code that has been given to it by aircraft traffic control and the aircraft's altitude. Now in ADS-B, it also actually responds to with a bunch of GPS information telling it where it is in space. So you even need a more powerful signal, and the aircraft is now responsible for telling the air traffic control system where it is in space. GPS receiver, pretty simple. It's where I am in space, but they have to be very sensitive ones because they actually have to be accurate down to feet because aircraft can actually use those to navigate through clouds, all the way down through clouds, so they can actually land on a runway moving about 100 miles an hour and nail exactly where they need to land on that runway without having to be able to see it at all. Electrical controller, so that's basically a device that will interface the controls within the cockpit of an aircraft with the flaps and trim system that I spoke to already. And then an autopilot. Autopilots on modern, especially larger aircraft, are very intelligent devices. You can actually have it fly the entire course for you if you want. And it'll actually maintain the aircraft's altitude. It'll maintain descent rate at a specific speed and a descent rate, as well as just keep you flat in the sky if you want to just keep going along the same direction. But they're typically controlled by servos that are directly connected to the control surfaces, and then the pilot can turn it on and off, and they'll have an autopilot control panel in their system that they can use to adjust everything. So any questions about avionics I've covered? Because it can kind of cover a little bit more when I start talking about how we can hack this stuff. Okay, so quick intro to CAN bus. CAN bus was a networking standard developed in the 80s primarily for use in automobiles. It's a shared medium, and the best way I can describe it is it's basically the way we were on the internet when it was initially created. Everybody could talk to everyone else, and everybody trusted what everyone else was saying. It's a shared medium, so it's like being on an Ethernet hub. You can see all the other messages on the CAN bus. It's just two wires that are twisted together with termination resistors on each end, and every device on the CAN bus is just tapped into that, and they can see everybody else's messages. It's very inexpensive because you can basically just take two wires, route it to all your components, and that is your communication medium. It's not complicated, doesn't involve switching gear or anything to basically act as a multiplexer. It is connected up and it works. It's very resistant to EMI because it basically uses differential signaling. Not going to get too far into that, but basically just have to know it'll work in high noise environments. So problems with it are any device on the CAN bus is going to trust any message it sees if it's actually looking for that message. So we have an inherent problem with that kind of trust model because you basically are trusting all the components that are on your bus. Is if you're a bad guy and you actually get on that bus, you can pretty much do what you want. So messages, the way they're constructed is they have basically an RFID, which is like an address, and data. So an address is not like a sender or receiver, it's just an address. Any device can send a message out on the CAN bus with a specific RFID, and then within the RFID, within the data packet, it'll actually have the data that it's wanting to send, which will typically be like signal levels. So we'll have things like oil pressure, airspeed, attitude, or any of the other various components, something that can tell something to turn on and off. So, hacking avionics. So a couple of years ago, I went to an air show down in Florida called Sun and Fun. It was actually right prior to a SANS conference and just happened to line up nicely. And to give you a little background on myself, I've taken pilot training. I've gotten to the point of soloing. Then some life stuff happened. So I've actually been in control of an aircraft myself. It's always been something I've been passionate about. I've always liked airplanes and aircraft and aviation. It's one of the reasons why I got involved with the Aviation Village this year, which anyone going to DEF CON should definitely check out. It's going to be our first year. It's going to be a lot of fun. Yeah. But I was at this air show, and I was looking at some people that were actually building an aircraft like what I'm building. It's called a Cozy Mark IV, if anyone's curious. It's basically a derivative of a Burt Rutan design with the elevator, the part that makes the aircraft go up and down. It's on the front. There's it's a unique shape. It looks really cool. I've always liked it. So they had just put in a modern glass cockpit system in this aircraft, and they were talking about how it uses CAN bus. And from my experience in hacking cars, I knew about CAN bus, I knew about the problems with CAN bus. I said, I wonder if this is subject to the same problems that automotive CAN bus is, which, you have the trust level and everything else. And so I started on this path. We got some avionics equipment in. We did the research on it. And then we started, Jen, a very long 2-year process working with the vendor and DHS and the appropriate authorities to actually release this in a very responsible manner. And it was good because we actually established a lot of contacts in the industry. We learned how to do this, and hopefully we paved the way that other people can actually do this research. Because all the stuff that I had done, people had done some stuff. Everyone knows about a tweet that was sent out that was on board a flight that may have gotten someone in trouble. I don't know if you're here in the room, Chris, but I've never actually met you in person. So, and we wanted to basically, say, we want to approach this. We want to be your friends. We want to actually make this secure so that the bad guys can actually do this and actually cause, loss of life or property here. So we went through this process. We did the disclosure, and then just last week we released our paper on a research on our blog. If you go to Rapid 7's blog, you can see it. It's talking about CAN bus and avionics. But we learned a lot, and hopefully we actually paved the road for everyone else to be able to do this responsibly and actually do this research. Because CAN bus is only one segment of a bus network used within avionics. There could be a bunch of other ones. We know that there's Ethernet out there. There's the airing standards. And I couldn't find any research that anyone done on any of these. So, have at it. Find a project you like, go at it, and do the research and work with the appropriate authorities and get that information out there so we can actually make these networks just as secure as the other networks that we're working on. So anyway, here are the caveats. If you're going to access CAN bus, you will require direct access to the CAN bus. So you have to have physical aircraft access. On an aircraft, that should be hard. On a small aircraft at an uncontrolled field, it won't be as hard as if it was, maybe down at McCarran going on one of the airliner's aircraft. But it does require physical access. However, that should not be the only control. You can't basically build an entire system that is this critical and say our physical accesses are one and only control around this system. Not something when it's this flight critical to life, safety, and property and everything else. And really what we discovered, there was no defense in depth on these systems that we looked at. We actually looked at multiple vendor systems when we did this research. So a couple of ways to get access. You're either an authorized person wanting to do bad, or you've snuck on somehow, and you've attached a device to these two wires, and it can be powered by itself. You don't need ground. You only need CAN high and CAN low, and now you're a trusted device on this network. You can do this with a small Raspberry Pi that has some telemetry link, or you can use something that's basically looking for logic, looking for particular conditions to be met, like altitude, GPS, and once either movie speed, that kind of scenario. Wait till you get above certain speed, arm, and then do your bad stuff. Or you can actually compromise the devices directly on the CAN bus. So we have devices now. You're seeing telemetry more and more. I was just looking at a system before coming in here that uses specific Wi-Fi SSIDs to do code uplinks and data uplinks, and this was on a small business jet system. So the Wi-Fi equipment was built right into the avionics, and it had a hard-coded SSID and hard-coded passphrase. It's actually right out there. You can find it if you know what you're looking for. So getting right into it, let me show you some example messages. So what I have right here are the arbitration ID. This is what's called an extended CAN ID because it's 10342200. That's in hex. And then we have bytes 1 and 2 are DE, actually bytes 1, 2, and 3, DE4714. So what I found is that from this ARB ID, DE4714 meant oil pressure. Now this was on a system that I built, and I just built up the telemetry for oil pressure, and I set up a little variable resistor on my kit so I could actually simulate the various oil pressure conditions. But A nominal oil pressure for the system was the data, the second half of this message. Actually, the first part that you see, the B2 is static, and then you can actually see it change here later. This is as I switch the message and switch the message down. If you notice, actually the number is going up. This is the most significant byte, and you can see it's going 60747B. So the number's increasing, but the oil pressure is actually decreasing. And why is it going backwards? This is my one and only joke on this, and I'll skip this. Because it's backwards. It was set up that way. Here's another example. This is a fuel level. You notice it uses the same arbitration ID, but now our first 3 bytes are DE4711. So instead of 11, it was 14. So the payload can actually identify the device that's actually giving the data, and then our data is actually in the second half of the message. This is a static one that's changing. You can see some small changes as it actually decreases here. But it didn't decrease so much to actually change the most significant byte here. So if we want to spoof these messages, all we have to do is create the false reading that we want. And this is actually a piece of software. It's different than what I used in the reports. I wanted to recreate it using a different tool. It's a tool called Vehicle Spy by Intrepid Control Systems. It's really good when you're wanting to reverse engineer CAN. So we basically just take these levels and we send them statically out on the wire, and we send them out at a rate that is faster than what the system itself is sending to. And if you go back, you can actually get, well, the screen doesn't actually show the timing, but what you need to do is actually look at how common the instrument sends it out, and you need to send your message out more common than that, because the most recent message wins. If you're thinking about telemetry, you're not going to trust the message that's 10 messages ago. You're going to trust the most recent one for your most recent signal. So if you're sending out a message more often than the basic instrument, you win. So quick demo. Okay, so this is a close-up of my instrumentation kit, and you can actually see these are the 2 variable potentiometers I put in to control the oil pressure, because I didn't actually have an oil pressure sending unit. But it's the same thing. It's a resistance that changes, and you'll see as it adjusts manually what happens to the signals. And you can see and you can't see past the quick time. Yeah, and you see both the fuel level and the oil pressure drop as I'm adjusting them down. So now we're going to drop the oil pressure just with a CAN message. Of course, you would have to go over here and it's funny. Okay, so now I'm just going to send this from the system. You're going to see it drop on its own. Oh wait, that's the wrong one. All right, I recorded the wrong video. I'm sorry I did this right before, but it works. I'm going to show you on the autopilot one. I'm going to show you on the. So we got to fix that one. Okay, so this is the actual telemetry system. And you can actually see as I'm sending the messages out. So the engine telemetry oil, you can see the messages come out, and you'll actually see a second one come out along with it with a static byte. Where's that guy? And you'll see it come onto the bus at a more common, more frequent level. But that's basically the system as it's showing it and as it's recording it. Let me check that video again, because I know I grabbed the right one. Actually, I have too many. Maybe I just played the same one over again. Right. You know, I think I do have it. I think I just recorded it wrong. try this. Yeah, no, I did record the video correctly. I just played the wrong one. Ha! You're still going to come over here. Okay. Get this out of the way. Okay, you can see it drop on its own. Haven't touched the instrumentation up there. That's just from sending CAN messages out on the wire. Yay, I did do it correctly. Okay. Moving on. Okay. Okay, back to our presentation. So the same thing. So now we have telemetry. We know we can spoof telemetry. That's going to cause a pilot to react. You know, he sees the oil pressure drop right away. He's going to look for an emergency airfield. He's going to divert. Now we have something a little bit more scary and active. And this is basically how the autopilot system on this particular system works. You have a static message for a steady state, which it's sending these out at a common rate about 10 times a second. And then when you engage the roll and pitch servos, because I only had 2 for this kit, you'll send this message come out. Basically, this means engage servos, and this 3 is 2 single bits to engage the 2 different servos. If I disconnect one servo from the system and remove it from the configuration, you'll see 0101. So each individual bit in the hex message represents a servo to tell it to turn on and off. And then when you disable it, it's just 01 again, and then 00 saying no servos. And that'll turn the autopilot system on and off. Okay, a little zoomed out. You can see my 2 servos attached to the top. I'm going to engage them. And this is through the interface right here. You'll see me actually reach over and turn them on. See, because I actually am telling to do something, you'll see the servo start to switch, and the other servo is resistant to me moving it. And now I'm going to do that through CAN. This is really hard to do at this angle. Reset from the beginning. Okay. And without touching it all, I'm just sending a CAN message, and the servos are going on and off. And what I'm doing is I'm actually manipulating the attitude heading sensor to actually get the servos to deflect in a particular way. Go ahead and replay that one more time so you can see the instrumentation change as I'm manipulating the gyros. So you can imagine you have a pilot in charge of this. Now all of a sudden the controls are fighting themselves, and he's telling the autopilot to turn off. There's usually a button right on the control stalk or a button up on the display to tell it to turn off, and they're not turning off because the bad guy is sending a message saying stay on, stay on, stay on, and how terrifying that could be. Really the only solution at this point is actually find the circuit breaker for it and actually pull power from the servos, assuming it's been wired appropriately to do that. So the next thing is just to kind of give you a quick intro to how the one system we looked at used a really complicated CAN messaging scheme and what we can do with it. This had a single arbitration ID, but it was like a multi-packet message. It was like a fragmented IP message. And then it used a separate but similar arbitration ID for data that was contained over the next several frames. So the first one, the header, included the payload size in bytes as one location. And then this basically contained all the data from the attitude heading reference system. So this is basically the sensor that's telling the instrumentation exactly how that aircraft is oriented in space. It also had the airspeed, angle of attack, altitude, temperature, because you need to use the temperature to actually calculate all those other ones. Saying there were basically two different messages. There were 60 byte messages, 50 times per second, and 52 byte messages, 10 times per second. The magnetometer and the GPS sensor also sent similar types of messages. This is an example. So we have, and then the gray is basically everything that's changing. These are values that stayed static in the messages, assuming this was one that meant something at the, until it was terminated. But 3C, which basically equates to 60 bytes, you'll see if you count it out, they're exactly 60 bytes here. These individual sensors, also with most significant bit on the right, or byte on the right, contained all the information that told the avionics, the aircraft's orientation and speed, the air altitude. And if you imagine, if you're a pilot, and all of a sudden your instrumentation is telling your aircraft you're pitching up, you're going to want to pitch down and actually compensate for that. If that's the only instrumentation that you have, it's going to be difficult. Now, typically aircraft have backup instrumentation, but some of the more modern ones, they trust everything that's actually coming in over this bus. If you imagine you're in IMC, which stands for Instrument Meteorological Conditions, and so you're in the clouds, you have no reference to the horizon. Or if it's nighttime, you have a reduced reference to the horizon. And if your aircraft is actually telling you you're 1,000 feet higher than what you actually are, you could be headed for a bad day very quickly. And then the way you would actually attack this. So basically you read in the header, you store the message size as a variable, you read the subsequent data frames into array, and then you replace just that segment of the data that you want and dump it back out on the wire. Because it's a more recent message, it'll be trusted. And you just have to do that more common than the existing system, or wait until the legitimate message comes in and immediately send your message afterwards. Because there's a bit of a timing thing there, but it's definitely a legitimate attack. I had it working out somewhat in Python, but it would get kind of flaky because I'm a horrible coder. But basically you could use this to do really, really bad things on an aircraft, and it's obviously a very scary attack vector. Now on one of the systems, they only used the single arbitration ID to carry all those values. That was trivial to hack. But even in a more complicated one where they've put a couple of controls in, I don't know if they consider this a security control, it was just the way they did it. If I had to guess, they basically received this, and they used a different method to transmit this data, and they downported it so it actually worked in CAN, so it was easier to implement. But some recommendations, we can't really say basically there's a problem. Okay, I see it. We'll stop now. So recommendations, quick glance. Sorry, I'd never done that, didn't see it over there. So we'll finish this up. And if you have questions, please come see me afterwards. I'll hang out for a couple minutes. Thank you.